Recording now. Yeah, thank you. This is the first talk of the John Conway Spirited Seminar Series of the year. So our today's speaker is Junaid Razzaq. Junaid Razzaq is pursuing his PhD from the University of Bologna, Italy, and the topic he's presenting is very much recent, Grassmannian Supermanifold, an introduction. So Grassmannians are uh, a kind of object which has enormous importance and widely studied in different disciplines, different branches of algebraic geometry and even differential geometry. But I think yeah, Grassmannian supermanifold is something even I'm not familiar with. So over to Junaid for a detailed introduction about Grassmannian supermanifold. Over to you, Junaid.
Okay, okay. So thank you very much. So it is an honor for me to speak at this John Conway Spirited Seminar Series. I am very thankful to all the especially Professor Imran Saib for giving me this opportunity to speak. So I'll talk about Grassmannian supermanifolds. And the way I make these slides is very introductory. So I'll not go into like very deep technical things, but I'll try to be very like at introductory level. Uh, so the talk is going to be in three parts. First of all, I'll describe classical Grassmannian manifolds, and then we have to do the similar thing in the supersetting. But before doing that, I have to tell you what do we mean by superset. So I'll give you a quick overview of supergeometry. Okay, so
Uh, Junaid, excuse me. Junaid, Junaid, we can't hear you.
what is a classical graph? So if you have any n-dimensional vector space, we take the quotient by this relation where we identify two vectors A and B if they are related to each other via a scalar. So if they are scalar multiple of each other. What we are
Excuse me,
actually doing
Junaid.
is we are trying to identify, yeah.
Junaid, can you turn off your video so that we can hear you properly? Because we skipped the part, the introduction, what you said, because there was no voice.
Okay. I'm sorry.
Yeah, so may you please start? Okay, from the basic definition once again.
Okay. Okay. So can you hear me now?
Yeah. Perfect. Go ahead.
Okay. So I am saying that classically a Grassmannian is the set. So if you have a vector space of dimension n, then the Grassmannian GKN is the set of all k-dimensional subspaces of V. Okay, you fix a k, and then you take all the subspaces of that fixed. So an elementary example is this projective space. So by that we mean that we take the quotient of our vector space with this relation where we identify two vectors if they are scalar multiple of each other. So what we are doing is we are trying to identify all the vectors that lie on same line. Okay, so we can identify this projective space as this Grassmannian 1, n. Right? So we are taking all one-dimensional subspaces of our vector space. Now, so if you have a homogeneous polynomial f in n variables, then it makes sense to ask whether f vanishes at a point p belongs to some this n minus one dimensional projective space. Because if you have a homogeneous polynomial and it is zero on some point, it is also zero on all the scalar multiples of it. So then we have this definition that a projective variety is the zero locus of some finite collection of homogeneous polynomial in a projective space, such that the ideal generated by these polynomials is prime ideal. So it means that your zero set is irreducible. Okay, oh, sorry, is there any question?
Perfect,
Okay.
perfect. Please go on.
Okay. Okay. So now, as an example of a projective variety, we can take this n-1 dimensional projective space. Okay. So any projective space is a projective variety. You can take it just as zero set of the zero polynomial. Now we know that from here, from this example, that we can identify this projective space as Grassmannian 1, n. Now the question is, can we realize all Grassmannians as projective varieties? We saw that the Grassmannian 1, n, they are projective, but can we realize all Grassmannians as projective varieties? The answer is yes. So we can always embed our Grassmannians into a projective space such that the image of the Grassmannian in this projective space is a zero set of some homogeneous polynomials. So how this embedding works? So we have this embedding, which we call Klucker embedding or Klucker map, where we take this Grassmannian and send it to the projectivization of the kth exterior power of V. Okay, we know that the dimension of this kth exterior power is n choose k. So the projectivization has dimension n choose -1. Now, the points in these Grassmannians are k-dimensional subspaces of an n-dimensional vector space V. So it means that if we take a W, k-dimensional subspace, and this W1 up to Wk is a basis of W, then this map sends W to the class of the wedge product of this basis. Now, you see, if you take a different basis, then by linear algebra, by basic linear algebra, you all know that the wedge product of two different bases will be related to each other via a scalar, which is just the determinant of the change of basis matrix. So it means that this map in this projectivization of this space, this map is going to be well defined. Now, there is this theorem which says that this Klucker map is in fact an embedding. Okay, so with this map, we have embedded our Grassmannian into this projective space. Now we have to see that there are some homogeneous polynomials whose zero set is the image of this Grassmannian. Now we take this particular case, G24. It is also for importance, is of importance for physicists. They call it complex conformal space. But also mathematically, this was the first case studied by Julius Klucker, and then some other mathematician developed the general theory. So by this G24, we mean all the two-dimensional subspaces of C4. Now, if you have any two-dimensional subspace W, so it means that it is generated by two vectors in C4. Okay, let's take them A and B. So, and A1, A2, A3, A4, and B1, B2, B3, B4, let's say they denote the coordinates of these vectors in C4. Now, you know that the wedge product of A and B will look like this thing. So these coordinates are given by the minors of this matrix. If you write A and B as rows of some matrix, then these coordinates of the wedge product will be given by the minors. And we call these coordinates as Klucker coordinates. Okay, so we denote it by Yij's, where Yij is giving us the minor formed by ith and jth column. Okay. So the image of this G24 in this projective space, which is P5, this is characterized by this single Pluk correlation. Okay, so in this case we have only one relation which like completely characterize the this Grassmannian G24. And the general case we have very similar. There are many, but they looks very similar to this one. So here I have written them. So if you have general Grassmannian GKN, then the Pluk correlations look like this thing. Okay, so where the sum is taken over all pairs obtained by interchanging a fixed set of k subscripts. Okay, now all this thing was just classical, very classical things in the algebraic geometry. We have to do similar things for the super case, but if you want to see more on, like, if you want to see all the technical details what I have said for these classical things, you can read the book by William Fulton. So the title is Young's Tabulux. Okay, now we have to go towards the supersetting. I'll give you a quick overview of supergeometry first. Now, the idea of supergeometry was in theoretical physics in the last century. So the idea is to extend classical geometry by allowing odd coordinates. By odd coordinates, I mean the coordinates that anti-commute. Like in classical setting, our coordinates are always commuting. But the idea of super geometry is to extend by allowing some more coordinates which will anti-commute. So the roots of this idea is lies in the idea of supersymmetry, but we'll not go into the physics side today. On the mathematical side, there is the foundational work by Manin and many other mathematicians, and some good reference books. I have added some good reference books at the end. Okay, so a super vector space is a Z2 graded vector space. So it means that we take a vector space as a direct sum of two subspaces. Okay, we fix two subspaces. We call the first one V0 as even part and the second one as odd part. And the dimension of a super vector space is denoted by this symbol P bar Q, where P is the dimension of the even part and Q is the dimension of the odd part. And we assign a number which is 0 or 1, depending on the even or odd. So to even elements, we assign 0, and to odd elements, we assign, this is called the parity. Sorry, if do someone do you have any question? Because
So far so good. Just
okay, no.
carry on, carry on.
Okay. So now, similarly, like similar to any category, for example, in the category of vector spaces, we have linear transformations. But here we have like a special kind of linear transformations which preserves the parity. Okay, so a morphism from a vector from a superspace V to another superspace V prime. It is a parity preserving linear map. Okay. So we denote this set by this sample home of V to V prime. And thus we have this category of super vector spaces where the objects are super vector spaces and the morphisms are these things. So also this category is, yes.
Junaid, any word about the field? Field can be any field here.
Okay, so in principle, yes, but for us, we are taking just the complex field.
Complex field. And secondly, any vector space can be viewed as a super vector space. This decomposition exists everywhere. So we can decompose any vector space.
Yes, you can always decompose, but you have to fix, right?
Mm-hmm. Okay.
Yeah. Okay. So this category of super vector spaces is a monoidal category. So there exists a tensor product which is given by this thing. So if you have two vector super vector spaces V and V prime, then the part of the tensor product is given by the like V naught tensor with V naught prime and V1 tensor with V1 prime. I mean, we are taking the tensor of the even with even and then odd with odd. And similarly, for the odd part, we are taking the tensor of with the even with odd and then odd with even. Okay. So
Junaid,
and then yeah,
excuse me. Can you
yes,
go to the previous slide?
yes,
Previous slide. Can you go to the previous slide? So is there any change? Next. Slide number 9.
yes, this one.
Yeah. So is there any change in the algebra of the vector space V over C will be as it is, or should it have to follow some
No,
algebraic
no,
diagram?
no. Okay, I will go. We'll discuss it next.
Okay.
Okay. Now, so a super algebra A is a super. Here I am discussing it. So a super algebra is a super vector space together with the multiplication morphism. Okay. But then here by morphism, we mean that it should preserve the parity. Okay. Because we are working in the category of super vector spaces. Now, a super algebra A from homogeneous X and Y belongs to A, we have this thing. Okay, in the classical setting, we have commutativity. Commutative algebra is the one where you have, but in the case, we have X, Y is equal to minus 1 raised to power the product of the parities times by X. It means for have X equal to Y. Any odd, sorry, if both are odd, you have X minus Y. If you have X, Y is equal to YX. Okay. So for the odd, you have anti-commutative.
Yeah,
Yeah.
Junaid, here by homogeneous, you mean regarding to the Z2 grading?
Yes. By homogeneous, I mean so it is not the like it is either even or odd,
Yeah,
not
regarding to
the
the
sum
Z2
of
grading.
both.
Yeah.
Yes. Okay. So as an example, we can consider this like this algebra, which looks similar to the polynomial algebra in the supersetting. So we have this free algebra with this coordinates t1 up to tp. These are even indeterminates, and then we have theta I days. They are odd. So similarly here, the even they follow the commutativity and the odd they follow anti-commutativity. So we take this free algebra and then quotient by these relations. So this is a commutative super algebra with these even. This is even part of it. Okay. Now, and is this the symmetric the like super version of the symmetric algebra which we have in the classical case. So we have this action of the symmetric group on the n copies of V. So the action is given by, it's very similar to the classical case, but here we have something different, that we have minus 1 raised to power a number. So what is this number? So if you switch to odd coordinates, so to odd vectors, we get a negative sign. So this number denotes so how many times you are switching vector. and we call it symmetric n power of this super vector space. Okay, so similarly, we have this exterior super algebra. This is defined by similarly, if you take the n copies of V and then you you quotient by this relation, where here instead of this subspace, we are taking this subspace, like similar to the classical situation. And then you define the exterior superalgebra as the sum, where you take the quotient by all of the n powers of beta n. Okay, so these was two examples, but then now similarly we can define a as we define in the ordinary case, and we say that we define this APQ as A tensor with K P bar Q, where by this symbol I mean I am taking P copies of the field as even part and Q copies of the field as odd part. Okay, so K naught is just the P copies of K, and Q naught, and K1 is just Q copies of K. So by the definition of the tensor product in like this, so an A module is said to be free if for some P and Q it is isomorphic to A or K. In other words, so an A module M is free if there exists some basis of M such that you can write even part as this thing and odd part as this thing. Okay, so in the even part, if you have an even vectors, its first P coordinates are even and last Q coordinates are odd, and if you have some odd vector, then its first P coordinates are odd and last Q coordinates are even. Do you have any question?
Yeah,
There was
so
some
far
noise.
so far so good. Junaid, what is the reason behind constructing all these things? Anyways, toward the end, this would be a good take for these kind of structure.
Yes, but
Maybe toward the end. Maybe toward the end, you can
yes,
continue if
yes.
you're explaining at the moment.
Okay. Now, so to now we have this morphisms for any free A modules. If you have two free A modules, A P bar Q to A R bar S, if you have a morphism, then if you fix a basis on both sides, we get a matrix similar as we get in the classical case. But now we have a particular kind of matrices which are 2 by 2 block matrices. You can saw it here. Okay, so because our morphisms have to preserve the parity, so we will get 2 by 2 block matrices. Okay, T1, T2, T3, and T4. Their sizes are given here. Now, so from here you can see that T1 and T4 will have odd and even entries, and T3 and T4 they will have odd entries. We call such matrices as even super matrices. Now, as in the classical case, if you have linear transformations, then you have a determinant. In the super case, we have something called Berezinian. Sometimes people also call it super determinant. Okay, the actual motivation behind the definition of Berezinian lies in the theory of integration over supermanifolds. So today we will not go towards that side, but we will just take it as a definition. Okay, so let us denote by this symbol as all the invertible even supermatrices of order P bar Q times P bar Q. And then this Berezinian of T is defined by this thing. Okay, So where by T1, T2, T4, and 3, I mean these things. Okay, so because our matrix is going to be a block matrix of 2 by 2 size, so we take the Berezinian in terms of these blocks. Now you see that it is very different than Berezinian. Sorry, it is very different than the determinant, because determinant is very nice. It is a polynomial. You can explicitly write the formulas, but here in terms of so if you write Berezinian, it is a rational function, and also you have to compute inverse of T4. So it is a bit difficult than the determinant, but it shares many properties with the determinant. So now also you see that, okay, so this is our definition, but with the theorem, you can prove actually that this first definition is equal to the second one. Okay, so these two are equal things. Now to make this definition work, we can see that at least T4 should be invertible. But now we have this theorem which guarantees us a bit stronger condition that a super matrix is invertible if and only if both T1 and T4 are invertible. Okay, and then we have this famous property, or which is very much like the determinant, that this Berezinian is multiplicative. So Berezinian of ST is equal to Berezinian of S times Berezinian of T. So the Berezinian is a homomorphism, these invertible supermatrices, to the even part of the non-zero even part of the this A. Okay, so these things looks similar to the determinant, but here I write two things which are different than determinant. The first one is that Berezinian is defined only for invertible module morphisms, while determinant is always defined. And the second one is that you can define determinant of a transformation T from V to V as a scalar by which T acts on the top exterior power of V, right? But we cannot define Berezinian like that, because there exists no top exterior powers of AP bar Q, because as I showed you before, that in the super case, the wedge of the odd with odd is not necessarily zero. Okay, but in the classical case, you know that if you have the wedge of vector with itself, it is going to be zero. Here in the super case, for the odd, we don't have this thing. Now, why I am trying to give, why I'm trying to do all this is because I want to tell you what type of spaces people study in the supergeometry. So this was all very basic, like a super version of the linear algebra. But now we'll go towards the definition of supermanifold. Okay, so if you have a topological space, then if you have taken a course in algebraic geometry, you know that a sheaf of commutative algebras is an assignment where to each open set of your topological space, you assign a commutative algebra such that if you is contained in V are two open sets, then there exists a morphism, we call it restriction morphism from f of V to f of U, such that these two conditions holds. And then we have the second thing, that if you have an open covering of any of your open set and a family Fi such that Fi restricted to Ui intersection Uj is equal to Fj restricted to Ui intersection Uj, then there exists a unique F belongs to this algebra F of U such that F restricted to Ui is equal to Fi. So even if you don't have taken any course on these type of things, but if you know if you know geometry, I hope you have understood what we are trying to do here. Okay, so we are trying to give another definition of a manifold. So a ringed space is a pair where this is a topological space, and this is F is a sheaf of commutative rings over M. And then we say that this pair is a locally ringed space if the stack Fx at each point is a local ring. Okay, I'm very sorry, I didn't add the definition of what do we mean by stack. Okay, so it somehow captures the captures how sheaf works at a point. Okay, so you actually have to take the direct, if you know some advanced algebra, it means that we take the direct limit of the uh, f of u for all the u's which contain our point x. But anyway, it is a way to assign a ring to each point. So if at each point this ring is a local ring, we call it a locally ringed space. Now, so now we have this alternative definition of manifold. So this pair is a real manifold of dimension n if it is locally isomorphic to Rn, and then this sheaf of smooth functions on Rn. Okay, now why we do all these things is that to define the super manifold, we replace everything here with the super thing. Okay, so a super ringed space is a pair where we have a topological space and a sheaf of super commutative rings over M. Okay, and a super space is a locally super ringed space. And then we define Rnm, which is our so what is a manifold? In the classical setting, you know, we have a basic model which is Rn or Cn. So we say that spaces that looks like Rn, they are manifolds, but in the super case, we first define our basic model. So how does this basic model looks like? So we take any open set in Rn and define this super algebra where this algebra is given by the smooth functions on V, and then we take the tensor product with the exterior algebra of these theta 1 up to theta n. And then we define this superspace Rn bar M to be the superspace where our topological space is Rn, but on and we have this sheaf of commutative super algebras, okay, which we define here. So now we have our basic model. So a supermanifold of dimension n bar M is a superspace which is locally isomorphic to Rn bar M. Okay, so similarly, this is just one thing I define in the super setting, but similarly with some other notions, these abstract notions, you can, for example, go towards algebraic settings as well. I mean, the algebraic super varieties. You have to, for example, here we are taking smooth functions. There in the algebraic categories, instead of these smooth functions, you will take polynomial rings. And then if you want to see it more geometrically, you have to use the notion of functor of points. But because I don't want to be more like, I don't want to go into the details of these abstract theories. We want to do something for the super Grassmannians. I just want to give you an idea how like how the super spaces looks like. Okay, a familiar example, which I hope to most of us is can understand it, that we take this odd tangent bundle of a manifold M. So you can consider it as a super manifold. So you know that if you locally, you can always write your differential forms as F times dxi wedge with dxj and so on. So it means that your manifold together with this sheaf of algebra of differential forms, this is a super manifold, and in the literature people call it odd tangent bundle. Okay, so that's it, enough abstract things. Now we will go towards the super Grassmannians. Okay, so now the first question is, are super Grassmannian projective? So before answering this question, a first try could be that does a straightforward analog of Plucker map works? I mean, just use the same map that we define in the ordinary setting. Let me recall what was it. So this was given by this thing that you take any basis and then you send it to the class of the wedge product. So does this thing works here? In the super case, the answer is if you want to see why, so you take this Grassmannian G12, 33. So if you take any L, which is a 1-2 dimensional space, it means that it is generated by one even and two odd vectors. So we have to send it to the class of their wedge product. So L goes to the wedge of V1 wedge with V1 hat, wedge with V2 hat. But then L is also a span of V1 and then V1 plus V2 hat and V2 hat. Now, if you send it to the wedge product, we get something like this. So the first thing matches with this one, but we have something extra. In the classical case, we don't have this type of situation, because in the classical case, if you have the wedge of two same vectors, it is going to be 0. But here, as I told you earlier, in the super case, the wedge of two odd vectors is not going to be 0. So even the projectivization will not work here. So, but okay, so the Plucker map, which we define in the classical case, will not work here. But can we define some other map which embed it into some projective superspace? The answer is no. So in general, these super Grassmannian, they are not projective. But to see the reason, we have to use some advanced arguments, which we will not go into the details. So if you are interested, you can use the book Manin or by Rita Fioresi. So in those books, they have given the argument. Okay, now, but there are some special classes of these super Grassmannians which are projective. For example, if here the main problem is because of the odd vectors. But if you take completely even planes, then going to be projective. So in the recent work is this, that last year, so we deal with this G2042 and explicitly computed the super Plucker relations and their quantum variance. So actually we was trying to model some space in physics, but along these lines we also computed these super Plucker relations. But so along the same time, these Ekiterina Shimyakova and Voronov, they have computed super Plucker relations for these Grassmannians. Okay, so completely even planes in some super vector space. So the idea for this class works very similar to the classical setting. You have to be a bit careful about the parities, but the more interesting thing is that they also try to give an analogous idea for the general super Grassmannians. We know that, as I told you earlier, that they are not projective in general, but what they do is they try to embed it into something that looks like projective. Okay, not projective, very different, but okay, I'll show you now. Okay, so before going to how they define the super Klucker embedding, I have to give you two definitions. That by super exterior power, this one we mean the set of all functions on R even and S odd covectors such that these two conditions holds. Okay, so I give you this definition just for the sake of completeness. We don't need it actually. So we just need a particular member of this family, which is they define it as a non-linear wedge product. So this is a function belongs to this family, which is given by the Berezinian. Okay, so if you have R even vectors and S odd vectors, then it is a function on R even and S odd covectors. You write your vectors as rows of a column, and you write your covectors as columns of a matrix, and then you compute here you are just computing the product of these two matrices, and then you compute the Berezinian. So they call it non-linear wedge product. Okay. In the classical case, we send our spaces to the wedge product of their basis, the class of wedge product their basis. Okay, so the first thing is try the same thing with this non-linear wedge product for the super Grassmannian. So if you take any RS dimensional space, it is given a span of R even and S odd vectors, and then we send it to the class case of these, which we define as non-linear wedge product. Now, if we take this Grassmannian G11 in 2, so it means that it is so all the space is generated by one even and one odd vector. So suppose let's say we have something like this, where this one is an even vector, this one is an odd vector. Then the corresponding the function is given by this symbol P of U, and then we want to see, can we recover back our U, these coordinates X, chi, eta, and Y, if we apply it on some basis vectors. So if you compute all these things, you see that we will recover only X. So the point is, as I told you, that the Berezinian is a homomorphism from the invertible, from the set of invertible supermatrices to the even part of the algebra. It means that the Berezinian is always going to give us even things. Okay, so somehow we will lose the odd information. So here, if we use this map, we will just recover X from here. Okay, now to recover Y, we can play a trick, which is just we will reverse the parity. Okay, by reversing the parity, I mean okay, sorry. So here we have this form of a supermatrix. By reversing the parity, we mean that we replace T1 with T4, we exchange them, and then we also exchange T2 with T3. Okay, this is the reversed parity matrix. Okay, so if we reverse the parity of matrix first, and then we compute this function, then we denote it by P star. So P star of U then will give us Y. Okay, so we have recovered X and Y. And now to recover chi and eta, they play an other trick. So they they say that we have to use wrong parity matrices. This Berezinian is actually multilinear in the even columns. So they say we can add wrong parity column in the even position. Okay, so such type of matrices, they call it wrong parity matrices. They call the odd column which they insert in at the even position, they call it ghost covector. So now if we do this, then we can see that here you see at the even positions we are actually putting odd covectors, so we can recover chi and eta. Okay, now observe so from all this the observation is that we can recover L provided we use both P and P star. Also, another thing is we need to extend the definition to allow these ghost covectors. So with all this thing, with this example, and these two things that here you can see, if you take a different basis, then the corresponding line of the change of basis matrix. So, but for the P star, the corresponding function is going to change by a scalar, which is the inverse of the Berezinian of the change of basis matrix. So this suggests to define super-Plücker embedding as this thing, where we embed this Grassmannian into a weighted projective space. Okay, classically we embed it into projective, but now because we need to use both of them, so and they are related with this thing, we this this projective space where this, I mean that is some of these two prime and G prime, right? If F is equal to times prime and G lambda inverse times G prime. So in the article, they prove that this map is an embedding, and they also computed the super-Plücker relations. So for this Grassmannian, G1 bar comma 1 into n bar comma m. So the super-Plücker relations looks like this. So which are not polynomials, but rational functions. And they have also given super-Plücker relations for general Grassmannian. And they looks very similar to these ones, but then you have to use a lot of indices, and it looks very long. I don't want to can. So that's it. This was interesting for me that they try to embed this Grassmannian into this weighted projective space. So okay, then in these are books there by Shemekov and Voronov. The title is on supercluster embedding and cluster algebras. And this was our article, this one, where we consider G2042. And in this article, they consider G2041. And in this book also, they consider G2041. So these are all the references for if you want to see the super Grassmannians. And here are some introductory books for supergeometry. This one is very famous, Gauge Field Theory and Complex Geometry by Manin. And also this one, so Mathematical Foundations of Supersymmetry. And there are some other books as well. So, okay, that's it. Thank you very much.
Thank you, Junaid. Thank you very much. Just a reminder for the audience that Manin passed away just, I think, in the last week. The last book you have shown, second last book, Manin, the book by Manin. Yeah, by
Really?
Manin. Yeah, he passed away a few days ago. In the last week, I think. It's a very interesting talk, Junaid. The topic was very, very interesting, but I'm flooded with too many questions. Let's first of all listen to others. So any questions, please go ahead. Junaid, there was an issue with your voice, but I think the slide was very clear. So for the ones who have the idea about the subject, the slide was quite elaborating, and I think yeah, we do have some difficulty in listening to you because there was a lot of distortion. But I
I'm
think
very
the slide was
sorry.
very clear. No, it's okay.
I am very sorry because I think there is some construction going on, and
Internet connectivity issues was an
also
issue.
there was some
Yeah.
internet
Yeah.
connectivity.
Any question from the audience? Please go ahead.
Hello.
Yeah, Suhail, go ahead.
Ji, assalamualaikum. Okay.
Walaikum assalam.
First of all, I was very
Walaikum
late
salam.
in attending the talk, so I'm sorry about that. So my questions are going to be very, 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 naive or something stupid question. So my first question is: are these algebraic varieties? So these, super Grassmannians?
No. I at the end was
Junaid, please turn off your camera so that you turn off your camera.
To see. Okay. So I was saying that no, these are not algebraic varieties. Okay, you have to go toward the super case. I mean, super varieties, they are not. All of them are not super varieties. But yes, there are some classes. For example, if you consider completely even planes in some super space, then yes, they are. So if you look at this article which I was presenting, in the first part, they consider only this case. They call it algebraic case. And then you can explicitly compute the supercluster relations, which are just polynomials. So these are going to be super varieties. But for the general, they are not. They are, as we saw at the end, that we embed it into some weighted projective space. And then you have something which is very analogous to the Klucker relations, but they are very difficult to handle. There are many variables, and instead of polynomials, you are going to have rational functions. So show you again. These are not polynomials, real life in right?
Yeah, Suhail, did you get the answer to your question?
I think there was a bit problem with the internet, but
Yeah,
the
there was a distortion. The answer is that in general they are not algebraic, but in particular cases, In fact, Junaid, try to imitate me because Suhail and everyone is having a bit of difficulty in
Mhm.
listening to. Please correct me if I'm wrong somewhere. Suhail, this kind of structure, they start up with some Z2 grading on the algebra with an even part and the odd part. And regarding to this particular grading, they built up a new structure which is not usual in usual setting. They are not algebraic, but there are particular cases where their results are algebraic. And in very particular cases that if one switch off one grading and assume as a single grading, the the newly grading they inducted C2 grading on the standard structure of algebraic geometry.
Okay, thank you, thank you.
Acha, Junaid, I have one question. What about what about the compatibility of the two grading? There is another component which is associated to algebraic variety, which started with the grading, particularly regarding to the Hilbert series and Hilbert function. So whether this kind of study has been studied, so particularly what I am assuming, so there will be Hilbert series is going to be split into two parts, the odd part and the even part, or something like that. Junaid, are you there? Yeah. Okay. Hello.
Hello, sorry, my internet connection is very bad.
Okay. Okay. Junaid, did you listen to my question? What I said?
No, 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 no. Can you please repeat it?
Do you know about the standard algebraic setting? We have the standard grading uh, on the algebraic set and
Hmm.
on the algebra, and then we have some invariants like Hilbert series in
Mm-hmm.
order to study the behavior of the variety, and lots of informations are coming through the Hilbert polynomial, Hilbert and Poincare polynomial. Whether the
Yes.
same kind of setting has been that grading is compatible with the grading you are doing, or it is going to split the Hilbert series into two parts. The even part has a different Hilbert series and the odd part has a different Hilbert series.
I think your last comment is more reasonable. I don't know about it in the super setting, but I think your last comment is more reasonable that for the even part, maybe you have another, and for the odd part, maybe you have another, but I am not sure.
And okay, Junaid, what are the benefit people are drawing from introducing the Z2 grading? I do understand the motivation lies with physics people. So
Hmm.
basically, super algebra, they already have a super algebra in Lie setting too. So in the Lie
Yeah.
algebra case, so
Yeah,
whether
yeah, yeah.
this super algebra is compatible with that Lie algebra setting algebra, this is an analog of it.
Yeah, 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 yeah. Of course. So in the super geometry, people are doing like two type of research. The first one is the one which I present to you, that you try to prove like the super version of the classical results. Okay, it is not always going to be easy. Okay? There are some things that are very straightforward analog of the classical situation, but on the other hand, there are many things that are not very similar to the classical case. For example, the one which we saw today, that in the classical case, Grassmannians, they are very nice. Even in the super case, they are very nice, but uh, before last year, there was not any such embedding into some weighted projective space or some kind of Pluk correlation. So one side is this thing that you try to prove super variant of the classical results, and the other side is you try to model some species of interest in physics. So with the idea of supersymmetry, there are many species in physics that don't fit into our classical geometry. So to fit those like models in physics in the class in the geometric setting, you need the idea of these super manifolds and the type of things. For example, the article that I was referring to, for like our article where we uh, studied this Grassmannian G20 in 42. So we was actually trying to model n is equal to 2 Minkowski superspace. Similarly, so these Grassmannians are also particularly important because, you know, as I said in the beginning, that this G24, this Grassmannian is also this classical Grassmannian it is of interest for physicists because so this is a complex conformal space. I hope you know about it somehow. So you can see your complex Minkowski as a dense subset sitting inside this complex conformal space. Similarly, in the after the idea of supersymmetry, there is this notion of Minkowski superspace. Similarly, there are notion of harmonic superspace, super twistor space. All these spaces, you can identify them with some super Grassmannians or more generally with some super flags. Okay, there is an article by a physicist. In that article, he identify many models with these super flags. So there are two type of research.
Mainly, Junaid, mainly I think the physicist people are pushing this particular boundary at the moment,
Which
particularly
one?
physics people, particularly.
Yes, of course, they are more towards physics. But for me, I think the one which is more mathematical, I like that one because I am from mathematical background, so I like to do this. It is very rigid.
Junaid, I didn't properly understand the topological setting when you was trying to introduce the sheave. So
Mhm.
particularly, the topology was the Zariski one. I don't think there is
No,
any change in that.
no. The classical one,
The
the
classic
standard
one.
topology. But when you are defining sheaf, you can take any topology, any topology.
Yeah. In for the sheaf setting, but
Yeah, but
regarding to
when you
the
define
but
many, yeah,
but regarding to the ring space structure, one has to stick with the Zariski one. Huh?
no. For when you are defining manifolds, you have to take the UL topology. But when, as I said in the talk, you can define similarly algebraic varieties, super varieties. Okay, so when you define super varieties, then you have to consider like the Zariski one. In the
Mm-hmm.
algebra, in the category of like algebraic things, you consider Zariski
Yeah.
topology.
And
But in
throughout in your talk, you were talking about the Zariski player, right? Or wrong?
uh, no, when I was defining super manifolds, I am referring to the standard topology.
Standard topology. Okay.
Yeah.
Okay. Okay. Is there any other question from the audience? Thank you, Junaid. Thank you for your answers. Are there any questions from the audience? Oh, okay. If this is the case, let us thank the speaker once again. Junaid, it was a very dense talk. I would say that you are very brave in presenting too many things in one talk, and definitely I do understand that it will be tough for many students to follow the whole lot. But this is
Mhm.
a very brave attempt to
Okay,
present too many
so
things in one lecture. I would suggest you to, whenever you are presenting this topic to other places, so dilute it a bit.
okay, okay. Thank you very much. But okay, so I was trying to draw the complete picture, and I
Yeah,
am
yeah,
very sorry
I understand. I understand.
if
I
any one
understand.
of you get bored during this seminar. But I was trying to complete a picture. I am very sorry if
No.
you
It's
don't
okay.
get
Thank
something.
you.
Yeah,
Thank you,
yeah.
everyone.
Thank you very much.
Thank you.
Thank you very much to all of you for your attention. I am very happy. Thank you very much.
Thank you.